In this video, we're going to cover part 2, where we're going to analyze the data for the aromatase dataset that we had collected in part 1. So in part 1 here, we have already collected the data from the CHEMBL database, and then we've downloaded the bioactivity dataset into our computer. And then what we're going to do today is we're going to take that data set and then we're going to prepare it into a form that is suitable for performing machine learning model building. And so if this is interesting to you, keep on watching. So the TLDR here is that we're preparing the bioactivity data of aromatase inhibitors so as to obtain a non-redundant data set, meaning that the data set does not have repetitive rows. And then we're going to use that for further analysis, for doing EDA, and also for building machine learning models. And we'll also build a Streamlit app as the culmination or the capstone project of the Bioinformatics from Scratch series. So here's an overview. So briefly, the overarching goal of this research project is to explore the structure-activity relationship for a large set of aromatase inhibitor. So in the first part of the series, I've already covered what is aromatase. Okay, so like the TLDR is that it is a target protein involved with breast cancer. And so the goal here is to collect the data set of potential drug candidates, and then we're going to make a prediction of the biological activity. So here, the first step is to compile a high-quality data set. So as in any typical projects for that is involving, like computational work, garbage in, garbage out. So in order to have high-quality model, we're going to need to have high-quality data. And so the bioactivity data for the aromatase target protein is provided from the CHEMBL database. And it has the accession number, or kind of like the ID number of CHEMBL 1978. And let's have a look here. If you go through each of the rows here, they're coming from individual research papers from the primary literature. So scientists who has already published the work in scientific articles, scientific journals. So they're aggregated in the CHEMBL database, and then we've already downloaded that data. All right, so let's proceed with the tutorial. So we're going to use the RDKit library. So what we're going to do here is we're going to connect to the Colab notebook. So links to this particular Colab notebook will be provided in the video description. So here we've already connected to the notebook, and then we're going to proceed to installing the RDKit Python library. So RDKit is a Python library that allows you to handle chemical data. So it takes Smiles notation, or like a two-dimensional representation, like a one-dimensional representation of a chemical structure, and then we're going to use that in order to compute unique molecular features or descriptors for the compound, and then we're going to use that for the machine learning model building. Okay, so other than that, it also provides common tasks that you would use for handling chemical data sets. And now we're going to take in the data that we had already downloaded from part 1, and then we're going to load it in to a pandas data frame. So here you're going to have a look at the imported data frame. So first column is the molecule CHEMBL ID. So the CHEMBL ID is like a unique identification number for each of the compound. So if you go here, each compound here has a unique CHEMBL ID. Okay. CHEMBL 1444 corresponds to letrozole, which is a FDA-approved drug. And likewise, 120374 corresponds to exemestane. And then the second column is the molecule name, and then you have the molecule max phase, molecular weight, rule of 5 violations, like how many violations to the rule of 5 are there. And the rule of 5 is simply also known as the Lipinski rule of 5. So if you search, the Lipinski rule of 5 is essentially a general criteria of drug-like properties. So what Lipinski did, Christopher Lipinski analyzed a large data set of orally available drugs. So drugs that are taken orally. And what he did was he discovered that the rules are multiples of 5, right? That there should be 5 hydrogen bond donors, 10 hydrogen bond acceptors, molecular weight greater than 500, and log P. But I think this should be molecular weight should not be greater than 500. So it should be less than 500. And a calculated log P should be, I presume, less than 5. Okay, so all of these would indicate the drug-like property. So if a compound has the property, then it's likely to be a drug or favorable drug that is, like absorbed into the body and it is cleared from the body in a reasonable amount of time and doesn't cause toxicity. Okay, so these are the computed properties here. So we have the molecular weight, right? It should be less than 500. And then we have the A log P. The other hydrogen bond donor acceptor could be computed using the RDKit library. And then we have the SMILES notation. So the SMILES notation here will allow us to go from this one-dimensional representation of the molecule. So it provides all of the chemical information of the molecule. And it allows us to deduce the two-dimensional and three-dimensional representation. Kind of like, how does it look like in 2 dimension? How does it look like in 3 dimension? Okay, and the best way to store it is as a SMILES notation. So that's how we could store the chemical structure information into a CSV format. And then we have other columns that tell us about the bioactivity data type, whether it is inhibition or IC50 or PIC50, and whether the target protein is a single protein or protein complex, and which paper was it taken from which journal, and which year. So that's more or less like the source of the data. All right, so we have already loaded in our data set to a df variable. And now let's take a look at the columns, right? So I've already gone through all of the columns for you here quickly. Yeah, so it has 47 columns and about 6,000 rows. So all of the 47 columns are provided here, but we're not going to use all of them. So we're going to use some of them for our analysis. So what we're going to do here is we're going to filter the data frame assigned to the F variable to keep only rows where there are CHEMBL value column having a non-null value, meaning that we don't want any rows without a value for the CHEMBL column. Okay, so we're going to remove all of the rows without the CHEMBL value. So if you scroll here, let's run it. If you scroll, okay, I think it's the CHEMBL is probably hidden in here in the triple dots here. So let's also add, in order to allow you to see it, let's add that, and then we should be able to see the values right there. So yeah, it's been reduced from 6,099 rows, I believe, to about 3,665 rows. So the remainder was removed. So if we were to take a look at the original data, if we change this to df, we'll see that some rows has a NaN value or a missing value. So we had already deleted that. And then the new data frame does not. Okay, so we have a complete data right there. All right. And now we're going to handle the duplicate molecules, because if you take a look carefully in the data set here, some chemical structure might look the same, it's because each of the row in the data here are independently reported from different research paper. And therefore, there's a high likelihood that many of the rows are the same and they are redundant. And that will pose an issue for our analysis when you have the same molecule, but then you have different biological data activity. So it has different bioactivity data values. So that will confuse the machine learning model once we get to the stage of analysis or model building. So what we're going to do is we're going to remove the duplicate. For your convenience, CHEMBL provides a column called potential duplicates. And although it is convenient to use, but then I'm not really sure whether that's a good idea because, like it's always nice to double check or at least, like perform in a more stringent way in order to make sure that duplicates are actually removed. Okay. So from here, we're going to see that CHEMBL identified 400 to be duplicates and 3265 to be unique molecules. Okay, so keep that in mind as we will proceed to analyzing the data on our own. Okay, so I think I might have switched that. It should be 0, okay, or most likely. Okay, so it is okay. So duplicates are roughly 400 rows. Okay, so 0 means it's not a duplicate, it's unique, and 1 means that it's a potential duplicate. Okay, so we're gonna keep rows having value of 0. Okay, so that allows us to have 3265 rows. Now we're gonna do it our way. Okay, we're gonna create our own way. So we're gonna leverage RDKit library to do that, to help us identify redundant molecule. So here we're gonna create 2 functions for analyzing molecular duplicate in the chemical data set. So the first function here, identify duplicate, will take in a data frame and the SMILE column as the input. Then we're gonna standardize the SMILE string because, like when it comes from different paper, the SMILE string might look different, but then in reality, they're like the same molecule. Or it might also be that the SMILE string might not be in a correct form, okay? And also, once we read in the SMILE string, we're going to generate the INCHI key, and the INCHI key will provide a good estimate of the uniqueness of the molecule. So in reality you have, like the same molecule, that same molecule could be represented by different SMILES notation. So therefore, that causes a problem, right? So if you have 2 SMILES notation that seemingly look different, but then in reality, they're the same molecule. So the INCHI key, irregardless of whether they have different SMILES, it will generate the same INCHI key. Okay, so if you have the same molecule but different SMILES notation that are representing the molecule, and when you generate the INCHI key, it will be the same INCHI key. Okay, so that will help us identify the duplicate molecule. And once we got the duplicate molecules identified, we're going to display a summary. And so we're going to do that using our get duplicate summary function. Okay, so it's going to provide a summary statistics of the duplicate removal. All right, so let's proceed to running this custom function. And we're using RDKit. And the identified duplicates is provided here. Right, so we're reading in the SMILES notation. And then we're going to make sure that it is a canonical SMILES. Canonical means it's considering all of the stereoisomeric representation, meaning the 3-dimensional way of how the chemical structure is represented. Because in 3-dimension, molecules are not flat like a paper, right? It might protrude outward to us or inward toward through a paper if we're representing it on a piece of paper. Then we have the next function here to calculate the INCHI key. And then we're going to put it into the data frame. and then we're going to populate the various columns, and then we're going to return the final data frame. And then the second function is we're going to just kind of display the summary stat of the potential duplicate molecule. So I think we already run this just to make sure, run it again. Okay, so we're going to apply the identify duplicate first, and then we're going to do the summary stat afterward. So here, we're going to take in the smiles column, and then that is our canonical smile representation. So we're representing the smiles again, canonically. And then we're bringing in the essentially new columns like inchy key. Yeah. So the canonical smiles right here. And then whether the molecule is valid. Is it duplicate, false, or true? So if it's true, it means that the molecule is duplicate. And if it is duplicate, we're going to assign a unique group number. And that unique group number will be given an occurrence count. So for example, if we have 7 molecules that are duplicates, we're going to give it a unique identification number, the group number here. And then the count will tell us how many duplicates are there. Here, for this group, there's 6 molecules that are duplicate. Okay, and so for each duplicate here, in the next stage, we're going to assign the mean value, okay, for the duplicate if there is variation amongst the 6 values here. Okay, however, if there's low variation, that's good. And then we're going to just, select the first occurrence. But if there is a high level of variation amongst the values that are duplicate, we're going to compute the mean value, and then we're going to use that for our analysis. And so in our final non-redundant data set is going to contain unique molecule on each row, and then it will contain the corresponding CHEMBL value, okay? Whether it's the actual CHEMBL value or if it's the mean value of the CHEMBL value, if the variation is low. Okay, so that's like in a nutshell of what we're doing here. So the summary stat is right here. So total molecule that are unique is 3665, and the molecules that are duplicate accounted for 1885. Okay, and groups with the most number of duplicate are 48. And there are simply, 2473 molecules that are unique. And then there are 1192 that are duplicate. And then finally, we're going to process the duplicate using our process duplicate function here. And then we're going to combine, the rows with 0 standard deviation and the non-zero standard deviation. And as I already mentioned, we're going to use the first occurrence, or we're going to use the mean value. So we're going to do that in this function. Okay, so we're running this, and then we're going to process it. And then the input columns are the inchy key and the CHEMBL value column. Give it some time, and it's finished. And now we're going to look at the summary stat here. So we have initially 3665 for the total initial compound, and there are 2473 unique inchy key. All right, so in a nutshell, we have a unique data set of 2,473. If you were to compare that to the estimated number provided from CHEMBL, from the CHEMBL database, there were 3,265. Okay, so there are a lot of duplicates in the data set, and we were able to narrow it down to 2473. Okay, so we believe this to be a high quality data set because we verify it through, conversion to a canonical version of the SMILES notation, and then identifying the true duplicate from the inchy key. Okay, so that is our breakdown of the data set. And then we're just gonna, standardize the column names here, giving it a lower character. And then we have the molecule CHEMBL ID, the canonical SMILE, the INCHI key, the p-CHEMBL value, and the document CHEMBL ID, just for reference if we want to go to the original source of the data. And then we're going to, in a nutshell, as the last step, we're going to save it into a CSV format called CHEMBL 1978, which is the accession ID for the aromatase enzyme provided here. ID of CHEMBL 1978. And our data is right here as CSV data right here. So I double clicked and it's read here. Yeah, so you could feel free to download this locally. And then we're going to use this for the future part of this Bioinformatics from Scratch series. So if you're finding value in the video, please support the channel by smashing the like button, subscribing to the channel, and also turn on notifications. And so all of the code are provided in the GitHub repo that is mentioned in the video description. And thank you for watching. And as always, the best way to do bioinformatics is to build projects. All right. And so see you next time.